All right. Ionic compounds are going to get 2 videos. This will be the first of those 2. They're going to get 2 because we need to be able to write the name from a formula, just like we did with molecular compounds. We also need to be able to write the formula from the name. Now with molecular compounds, you have the prefix, you have the elements, and so it's easy enough to go from the name to the formula. There's a little bit of a trick with ionic compounds because we're going to have to worry about how many negative and positive charges there are. So that's going to be its own separate video. So this first one, we're going to talk about the nomenclature rules for ionic compounds and why they're different from molecular compounds. So if you look at my picture here that has green and purple dots, the little dots are sodium cations and then the green dots are chloride anions. They come together in a very special ordered array. You can see that there's 6 nearest neighbors. You can see that everything looks like it has its own special spot in this lattice, and that's the way all ionic salts are going to work for us. That also means that we don't have molecules here, and really we don't even have discrete formula units. It's never that we can pull out a sodium chloride. We never think of a sodium ion and a chloride ion as a salt. It's an array of those 2. So we're going to go all the way down to the formula unit here. That formula unit is going to be the smallest discrete ratio we can get this down to. Now for sodium chloride, there happens to be 1 positive charge and 1 negative charge. So that discrete unit's in a 1-to-1 ratio. And so sodium chloride would be the formula unit that we would write for this. We'll get into that more as we move forward. So if you can't do that yet, don't worry about it. Now these salts are formed by electrostatic attractions. There's not an actual sharing of electron or not an actual bond here like we had in the molecular compounds. So because of that and because there's distinct areas of charge, we're going to have a different set of naming rules here than we did before. Different types of compounds, different types of rules. Our rules are going to be based on the fact that there must be cations and anions present. So we have a positively charged thing with a set charge and a negatively charged thing with a set charge. There's going to be an ordered number of those. So there's going to be 1 ratio we can get to, only 1 ratio we can get to. That's going to dictate the name. So as kind of an aside, you're used to the term table salt. And this is actually the salt that you guys think of when you think of table salts. It's sodium chloride. But any cation-anion pair that comes together in pretty much any ratio, the chemist is going to call a salt. That term salt's just going to describe an ionic compound. All right, so that last slide said that we have cations and anions that come together. We never have 2 cations that come together. We never have 2 anions that come together. We have some number of cations and anions that come together in order to make a neutral compound. The cation is the positively charged species. So there was an atom. That atom lost 1 or more electrons, and it became positively charged once there were more protons than there were electrons. Now this example is sodium, and sodium loses a single electron, but not all of our positively charged things have a +1 charge. They can go up to 8 if we really want them to. 7 actually isn't that uncommon because manganese compounds usually involve a 7 coordinate or a +7 manganese. Now on the left side of my equation, I have an atom of sodium. That atom has the same number of protons as it does electrons. That means overall, this would come out to be neutrally charged because it has the same number of positive charges as it does negative charges. On the right side of my equation, that's not the case because right now this sodium still has 11 protons because the number of protons define the atom. If I change the number of protons, I'd no longer have sodium. So this number can't change. That's a bit of a review. But now, since I lost this electron, my sodium atom only has 10 electrons to it. That's 1 more positive charge than negative charges, and I come out with this positive charge overall. Again, you could have a 2+, a 3+, 4+, up to 7+ without really thinking too hard about it. Anions, on the other hand, are going to have a negative electrical charge, and that's because you start with an atom, and that atom actually gains electrons. So in the case of the oxide ion, we saw this when we talked about molecular nomenclature. An oxygen atom is going to gain 2 electrons and give you an O2 minus ion. For this atom, we have the same number of protons as we do electrons, and again, that atom will be neutral. But then on the right or product side, we have 8 protons. Again, it's oxygen. It cannot change the number of protons. But now we have 10 electrons. So we have 2 extra negative charges. And overall, my ion has a charge of -2. We're going to have to know what atoms make common charges, and we'll see a periodic table later, in order to know how many to put together. Okay, so keep that in mind, that you have to have some idea how cations are formed and some idea how anions are formed, moving through this video and the next one. All right, so here's a little preview of some ionic compounds. We have this first column here are cations. Again, we saw sodium, lithium, and potassium are going to go that same loss of a single electron. And then here we have zinc and calcium, which actually undergo the loss of 2 electrons. In our anion column, we have a variety of charges as well, -1, -2, and -3. If you look at the chemical formula, you will notice that in all cases, these cations come first. And we'll see another slide. But when we name things, the cation comes first. We're always going to think positive and then assume things fall apart and move to the negative. But our cation is going to be the first part of our name, and then the anion is going to be the second part of our name. Just like molecular nomenclature, we have a 2-word name. On the next few slides, we'll show you what to do with the cation names and what to do with the anion names. And then when you get over here to the compound name, you're just going to stick that cation name with the anion name and be all done. So these questions down here, the cation is always listed first. Again, think positive to begin with. The name of that cation, as we'll see on one of the next slides, is just going to be related to the element. So we're going to take the name of the element and stick cation behind it. Again, we'll see that a little bit more later. These, if you'll look at them, are all ions derived from elements on the periodic table. And they all have the same IDE ending that we used in molecular nomenclature. So they're all going to have the same ending. That means that you have one set of things to learn for both of the rules. So that's kind of convenient. Again, this is just for elements or ions formed from elements on the periodic table. All right, you cannot form a name for an ionic compound unless you can name the pieces. So we're going to name cations and anions. We're going to do it in the order they show up in our name, which means that this one's going to be first and this one's going to be second. All right, if we have main group, remember that's group 1 and 2, I'm going to write aluminum here as well. Okay, and aluminum is going to have 3 plus as we see it in a minute. This is actually in group 3. These main group ions are going to just use the name of the element. So here I wrote Al3 plus. This would end up being the aluminum cation. Okay, so we take the name of the element, we stick cation behind it. Now these main group elements make a single charge. They lose the same number of electrons every time they make an ion. So we don't have to do anything fancy. And if I hear lithium cation in my head, I know that that lithium has lost a single electron, so it must have a positive 1 charge. Okay. If I hear strontium cation, this is in group 2, I know that it makes a positive 2 cation. One of your jobs when we get to see the periodic table in a little bit is to learn the common charges, and these are 2 terribly common charges, of the main group elements. Now we can move to the middle of the periodic table where the transition metals are. And now there's nothing common because these guys don't play well with everyone else in the sandbox. The problem with the transition metals is that they don't always lose the same number of electrons. So they don't always have the same positive charge. Copper, for instance, can lose a single electron and become copper 1, or it can lose 2 electrons and become copper 2. The chemist needs to know the difference between those two because they're probably 2 different bottles on the shelf. So the way we note this is that we give a Roman numeral. That Roman numeral indicates the charge, and we put that in the parentheses behind the name. So if you see here, we have copper plus. This guy has lost a single electron, and it has gained a +1 charge because there are 1 more protons than there are electrons now. So if I were to make a compound of this guy with chloride, it would have a single chloride, and the chemist would need to know to look up copper 1 chloride. Now when you get to Al, note that there is no space right here. I believe Al gives you a hard time if you put a space there. Note also that these are capitalized. Do not use lowercase Roman numerals. These are going to be capital Roman numerals. When you read this out loud, it's the copper 1 cation. If it was part of a copper chloride, it would be a copper 1 chloride. We don't have to use Roman numerals with the main group because they can only form 1 charge. They lose the same number of electrons every time. They are predictable. They only do the one thing. And so in these cases, the Roman numerals would be redundant. So we don't use them. We're only going to use them when the transition metal can change oxidation states. So at least one more note about Al. Zinc is found in the transition metals, and silver is also found in the transition metals. But silver really only has a +1 charge. That's what it does. And zinc really only has a +2 charge. I believe that Al gives you a hard time if you use Roman numerals with either of these. So if you type one in and you put zinc 2 chloride and it doesn't like it, get rid of the 2 and just try and doing these. If there's not more than 1 possible charge, we tend not to include the Roman numeral. So the anions in ionic compounds, if they are ions formed from elements, which we refer to as monatomic ions. Okay. If they are ions formed from elements, then we're going to use those same IDE endings that we saw with molecular compounds. So you should already have a set of flashcards because you already have those videos. But if you haven't done that yet, put these guys on flashcards. Make a note that ionic nomenclature and molecular nomenclature are going to use the same rules here for monatomic anions. Monatomic anions. Okay. Now, here's our periodic table that I promised you. Remember that when we were talking, I don't know what happened. Remember what we were talking about, the periodic table, we said, okay, everything that was in a column behaved similarly, at least in those main groups, okay? Now, the reason for that is that if you'll notice, all of these in this first column, these alkali metals, have lost the same number of electrons, so they all have a common charge of +1. That common charge of +1 helps to dictate that all their chemistry will be roughly the same. So when you get your periodic table on an exam, what you are going to do is grab it, and one of the first things you're going to do is put +1 on that column and +2 on this column. Because these guys here, these alkali metals, want to lose 1 electron that gets them to a noble gas configuration, which we will talk more about later. This second group is going to lose 2 electrons to get to that configuration. 2 electrons make it happy. When it loses 2 electrons, it ends up with a +2 charge. We have aluminum over here, and that's really the only +3 that you need to know about. But here we have a +3 charge. We're not really going to think of boron here because boron forms more covalent compounds than it does ionic compounds. I'm going to move over here to group 7. These guys are going to be -1. They gain a single electron, and that makes them pretty happy. The oxygen column, or the chalcogens, we didn't go over that name, but it's a fun name, so I use it, are going to be -2. They gain 2 electrons before they get to that noble gas configuration. This nitrogen column is going to gain 3 electrons before it gets to that noble gas configuration. And carbon actually could gain or lose 4. That says 4-, but it could gain or lose 4. So we're not going to worry much here. We're not worried that much about carbon. Carbon gets its own class. You can worry about carbon when you get to organic. You are responsible for knowing all of these common charges that I have written across the top, which, with the exception of that carbon column. Now, here we go. These areas here, these blue ones, everything that's in the transition metal block, we can assume at least could change oxidation state. Here are your Roman numeral elements. So when you name these, you're going to use Roman numerals with the exceptions that I mentioned. Some of these guys really only have one common charge, and I think Al gives you a hard time about these two. This table is a little misleading anyway. Manganese has a bunch of charges. There's manganese 4+ is relatively common, and 7+ is relatively common. So there's not a single charge. If you put a Roman numeral with any of these transition metals on a free response kind of question, you would get credit for it. We will just assume everything in this block can have a more than one charge. And Al may give you a hard time, but I won't. How about that? Okay. All right. So you have to be able to recognize cations and anions. With a list like this, one of the easiest things to do is look for these endings. These IDE endings imply that they are anions. We saw those on that slide, right? We could also look at the periodic table. Here's a crappy periodic table for you. You're welcome. Here's my stair step. These guys up here were nonmetals. My nonmetals form anions for me. And if I looked up bromide, selenide, and oxide, they're all going to be there in the non-metal column. And the other ones, right, magnesium's here-ish, and then cesium's down here somewhere, and barium's down here somewhere. So these, E, F, and A, are all metals. Metals are going to form cations. When we put those in compounds, we're always going to put the cation first. So if we look at the bottom of the screen, you'll note that the cation, or the metal species, is always coming first. These guys over here are all non-metal species, and they're all listed second. Now, we don't just have monatomic ions. Sometimes we have groups of atoms that come together, and those groups of atoms, when they come together, always kind of fall under the same electronic conditions, and they end up, the way the electrons are shared among them, with an electrical charge. So these are groups of atoms that are always going to stay together. They really don't come apart. And they're going to carry some standard charge. That charge isn't going to change. So if we have an S and 4 oxygens, SO4, they're always going to come together in such a way that has a 2- charge. Now, there are a lot of these. Your book has a really big table. This table isn't small, but you will be expected to know these for your exam. We can't really be a literate chemist without knowing what things are called. I'm going to assume that you have studied these, especially as we move on through the course. And if I say potassium permanganate, I expect that you can say KMNO4. That requires you to memorize all of these things. Memorizing all of these things is probably going to involve some flashcards. You'll be responsible for the formula and the charge and the name, and going back and forth between any of those three. It's worthless to know what the formula is if you aren't sure what the charge is, because we're going to have to balance charges in the next video to write our formulas. So you have to know all three pieces, and you have to know them well. Every now and then we're going to get kind of tricky, like in this block here. We have 4 things that are pretty close to each other. They all come from acids, and there's a different number of oxygens, and then there's a number of oxygen rules. If you memorize those from the book, great. I don't think it's that useful for us, really. But we do have things in here where it's really easy to get confused, because you have ClO, ClO2, ClO3, ClO4. Luckily, they all have the same -1 charge, but then all 4 of those related but different anions have related but different names. So your job is really going to be to work hard on these. Now, this is usually where students slack off and they don't believe me and they miss these questions on the exam. So I really encourage you to go through with some flashcards and learn them. This one down here, this hydronium cation, note there's only 2 cations to begin with. And I'm going to take one off your plate. It's here because we use it extensively in 117, so it's worth you recognizing it. For this part of the course where we're naming things, I'm not going to put it in a compound. So the chances of you naming an ionic compound with a hydronium ion is not super great. Not the case with ammonium. This one is really common. It forms a lot of compounds. It's related to ammonia, which is NH3. Ammonia is relatively common and used in a lot of compounds. So this one is a definite learn me. This one you can probably hold off. All right, which one is named correctly? Well, fluorine depicts an atom. That names an atom. F- is fluoride. Okay, not fluoride. Remember that our spelling counts. SO3 2-, if I go back here, I have SO3 2-, which is sulfite, not sulfide. Okay, sulfide would be S2-. So that one wasn't right. That one wasn't right. Hopefully C is. If I look up Br-, it should in fact be bromide. All right, this one here, matching things. Sulfite, we just looked up, and that should be SO3 2-. It involves more than one atom, so it is polyatomic. It does have a negative charge, so it is in fact an anion. OH- is a hydroxide, but it involves more than one atom, even though it only involves 2. So it is polyatomic. I would assume this one is right, but you always want to double check. Carbonate is in fact CO3 2-. It is in fact polyatomic because it involves more than one atom. It has a negative charge, so it is an anion. Ammonium comes from ammonia, and so NH4+ looks like a reasonable formula for ammonium. Involves both nitrogens and hydrogens, so it must be polyatomic. It has a +1 charge, so it must be a cation. That's your polyatomic cation that you need to know. Here we have a monatomic cation, or a metal ion. We've got magnesium, magnesium 2+. It is in the second column, so that looks okay. It is monatomic, and it is positively charged. So we got check marks everywhere but B, and B must be my right answer because I'm looking for the one with the error. All right, so now we can name the pieces, which is great. You gotta be able to put the pieces together. So you name the cation, you name the anion, and then you stick them together unless it has cation behind the cation's name, and then you drop that part. So here's a list of 4. Sodium is in the first column, the alkali metals, so it forms a +1 cation. The name of that cation, therefore, is sodium cation or sodium ion, whichever one you like. Chloride is in the 7th column. It gains 1 electron. I believe Al may want you to put chloride ion instead of just chloride. I'm okay with just chloride. We name that sodium chloride then, because we leave this off, we leave that off, and we put together what is left, which looks a lot like sodium chloride. Here in the middle, we have copper chloride and copper chloride. The difference is this one has a different subscript than the first one. Now when you get to transition metals, you may or may not know the charge on the copper. And if you know that Cl is -1, and we do because I just showed that to you, then it makes this easy enough. But here's the process of figuring it out. Here I have 1 copper, right? So we'll say that. And I have 1 chloride. Overall, all of these compounds have to come out with a neutral charge because it is in fact a compound. So I got to come up with the same positives as I do negatives. Well, I still don't know what the charge on the copper is, so I'm going to call that X in my equation here. And I know I have one thing that has a -1 charge, and that overall it has to equal 0. So I can solve for X, and I can say X is +1, where X is the charge on the copper. So this charge must be +1, this charge must be -1. That makes some sense. There's one of each. That gives me a neutral compound. Because it's the transition metal, I have to remember my Roman numeral with the charge. So I'm going to have copper 1 chloride. Again, there's no space between the name and the parenthesis, and the Roman numeral is capitalized. I have to do a similar process for the copper 2 chloride, which, whoops, I don't have 2 coppers. I have copper, and I have 2 chlorides, and again it has to add up to 0 because overall I have to have no charge on the overall compound. I still don't know copper. Whoops, that's a plus sign. I have 2 things with a -1 charge. Overall it has to be neutral. X ends up being +2. Again, that's the charge on the copper. I must need a Roman numeral 2. I have a Roman numeral 2. Last one there, I have magnesium, and I have a polyatomic ion, which is phosphate. So I have the magnesium cation, phosphate anion, put them together, you get magnesium phosphate. Now note that we are not indicating how many of each there are. There's one way in which these ionic compounds come together, and that's it. There's one ratio of cations to anions. You don't have any other choices. So we don't use prefixes here. We don't use any other means to tell us how many. Everything that we need to know is buried in that name. And we'll move from the name to the formula in the next video, so you'll know how to do that. But there are prefixes in molecular nomenclature, because there is a sharing of electrons. There's not a charge transfer. Electrons can be shared in different ways, and different atoms can come together in different ratios. And so in molecular compounds, we have to have a prefix to denote how many. In ionic compounds, we have a positive charge of some magnitude. We have a negative charge of some magnitude, may or may not be the same. But those magnitudes, we got to figure it out. We got to come up with the same number of positive and negative charges, and there is only one ratio of those two that will give us a neutral compound. So we do not have any type of prefix or indication of how many in ionic nomenclature. It's a pretty common mistake on an exam, so make sure you make a note of it. All right, this is actually where we will start the next video.